This last hour is really a discussion, a little bit more about technology in the big data space, so for processing data. And it will be about, as well, so we've looked at batch processing. We're going to talk a bit about stream processing, give a couple of examples. I won't really run anything, but we'll look at some code examples and understand some of the concepts where how things are developing, up until some of the very latest stuff, which is Beam, comes from Google very recently, some of the work that they have released out into the public, right? For now it's become an Apache project. So a lot of these things have become Apache projects, which makes them open for us all to use and contribute to and so on. And hopefully that will give a reasonable idea of what's happening. So Apache Spark we will look at first, and it comes after MapReduce, so it's essentially using the same sort of concepts as MapReduce, but it's a lot more optimized. And it was created by AMP Lab, I think, and Berkeley is very much involved with it. It was written in another language called Scala. I haven't really used Scala myself, but it's good for distributed systems, right? Building distributed systems. Although a lot of that's being replaced now. People find it a bit hard, so a lot of it's being rewritten in Java and so on. So this system as well, there's this another kind of resource management system called Mesos, which is a bit like Yarn that Hadoop provides, was built, and it was kind of tested on that. And the focus of this was iterative programs, like machine learning type things, interactive querying, and I guess really what people were trying to do around this time was to unify a number of things that were kind of missing from the MapReduce. So MapReduce gave us batch processing, on Hadoop, and that was very good. On the Hadoop file system, it was a way of very cheaply, affordably storing large amount of data reliably and processing it, that data, whatever you had stored, right? But that's, by batch processing we really mean, we have a fixed data set. It's not changing. Here's the data set. It could be it could be a petabyte of data. It could be a really large amount of data. But it's fixed, right, during the processing, and we're going to now process it, and it doesn't change, right? So, but that and that was at a time maybe when the velocity of the data wasn't so important, or it wasn't being focused on. So the changes in the data weren't the focus. The focus was just on we've got so much data. Google had gone and collected all this stuff about the internet, and all the pages, and they had all the data. It was a huge amount of data, and the focus was on size. But there are other things that sort of started becoming important, because one of them is that the data is constantly changing. It really is. You're always getting more data coming, really, and the notion of trying to think that I just have one data set that I want to process, as big as it may be, becomes a bit cumbersome as well. People started to see that we want results as new data arise, right? So in some cases like financial trading, or if we're doing security, like I don't mean like cryptography, but I mean like surveillance or trying to understand a population, monitoring and trying to respond to things quickly. Then as all this data, you need to respond to it maybe within hours, right? You can't sort of think, oh, well, at the end of the day it will be okay or something like that. The sooner that you can respond, the better. And so the notion of time became very important, and that we need to be able to process actually the data as it arrives, right? So as every little piece of data comes in, then do something with it. You start looking at incremental algorithms, where you can change the result simply with a change in the data. You don't have to rerun the process over the data again, as if you forget everything and then do it again and run again. But an incremental algorithm allows you, with a small change, say in a graph, instead of having to, if you're computing the spanning tree, you don't have to go and recompute again from scratch. If you change one edge in the graph, you can compute the new spanning tree with the minimum number of computations based on the fact that you already know what the existing spanning tree is. Now, incremental algorithms are not necessarily easy to do for all kinds of problems, but that is the way that we are going. Incremental algorithms, so that we take each piece of data and then apply it to what we have. And what we have typically might be sitting in memory or on disk somehow, a result that we want to update. So there's the streaming part. The other thing there is that we always tend to think of bounded memory algorithms too, because ultimately, as more and more data comes, and we have this problem with our existing systems, that we have things that construct graphs and so on, and the memory just keeps growing, and eventually it fills up more than even our distributed system can, the resources that we have. And at that point, what do we do? So, right now it's throwing an exception and it's just clearing the memory and then it's starting again. But really we need a way of degrading gracefully. If we start running out of storage space, what should we remove? The oldest parts of the graph, perhaps, or maybe there are better choices we can make. So there's a lot of interesting things when you think about processing data as it arrives, rather than building up a batch of data, and then processing that as one unit. And then as well, people want to be interactive. So the people that are seeing the results of this data, eventually it's being seen by somebody. You're not just processing it and throwing the result away, but the result is being seen by people, and those people are responding, and sending back. Maybe they're changing parameters, or they're somehow they want to view the result in different ways. Or in our case, for example, there are operators that look at the information that comes, and they might select certain people that they see, or groups or clusters of people, and then say, let's focus on that, or and the whole system changes as a result. The processing changes, everything changes, and so the interactivity is a kind of important part as well. And coming back to just Hadoop and MapReduce, it kind of didn't really, it's just processing and storing data and processing, which is very good at what it does, at what it was designed to do, but it doesn't really address these other things. So people started doing that, thinking, how can we do that? And Spark is an example of that. And then even more thinking comes later. We see with Beam, still more problems to be solved in this space. So that's kind of why people started building Spark. Just to sort of dig into a little bit about Spark, so it's trying to do unification, and it has this thing called a resilient distributed data set, and all of the processing in Spark sort of uses this resilient distributed data set, right? And it's just a read-only partition collection of records. The partitions help that it that it can be parallelized, so you need more partitions in order to parallelize, to map it out to the different nodes. It's read-only because that just makes, from a reliability, it makes things simpler, that we don't need to worry about concurrent updates and stuff like that. You can add to the data set, you can kind of add more elements, but you never really remove things, right? So they can be created through processes like reading things from a drive or from somewhere. You create a resilient, an RDD, and then from that you apply some transforms, as we see. So you can cache HDFS data, and this is another change, I guess, in the way things work. So the guys at Berkeley and that, they're sort of thinking, that instead of always putting results to disk and then reading from disk and putting to disk, that let's just put everything in memory and do the same kind of thing as the MapReduce iterations, but working in memory. So I mean, I think that, but it's still having fault tolerance as well. So here was the iterative process that in MapReduce, that you have some HDFS read for the mapping part. There's a couple of iterations here, and then it says at the end of the iteration it wrote the tuples to a disk HDFS write. Actually, in the former slides, I think it showed that these tasks just wrote to the local disk. That was kind of the way the slides were showing. But in any case, they're writing to disk, and then the reduced tasks would read from that, and then the result that would be written to the disk. And if you had more iterations, you'd be reading then for the next map reduce from the disk, and so on, right? So there was actually this kind of reading and writing from disk. So one of the changes with Spark is that the data is read from disk, and then if you have many iterations to do the processing, everything then is just kept in distributed memory, which is very much like your distributed storage on the disk, but now it's kind of one more level up. So if you remember the memory hierarchy we talked about, right? So there's the RAM up here, and then the secondary storage. And I think you could even break the secondary storage up if you wanted into solid state. Yeah, I wasn't thinking solid state drives and hard disk drives in some sense, right? So the RAM is a bit faster. It's the fastest way. Solid state drives are catching up because they're like RAM anyway, really. When you think and so they're quite fast. And then the hard disk drives. So you kind of, in some sense, I mean, this diagram's really just saying there's disk and there's RAM, right? But you could even split it up a bit more if you wanted. And I guess one of the directions, and I won't be here tomorrow, unfortunately. I'm going to Agra. It seems like I'll be doing a little touring. But one of the directions you might think about is memory hierarchy when you have your discussion tomorrow and conclusions and so on, and coding at the different levels and moving data. From when you do this, that this data now is very hot data. This is the hot data, and the hot data is in memory, whereas before we were thinking of the hot data we still had on the disk. But now really the hot data you could consider in memory, and maybe warm data is on the SSDs, and the cold data comes down to the HDD, and so different codes at the different levels, and then what is the cost of taking something that's coded at one level and recoding it, accessing it and bringing it up to the next level and recoding it at that level. And can you do that? Can you prefetch it, if you know that it's going to be needed in advance, and then you have to bring that into the memory, which is your fastest, and so on. So and that'll probably be, that will probably be where you have the replication now. We'll move up into the RAM rather than, I'm just speculating, right? I mean, and maybe people are working in these directions. And you might do a bit more searching for research papers and see what's going on, right? So Spark is kind of doing this, right? And from a performance comparison point of view, you can see obviously it's going to do a lot better if instead of reading and writing to the disk drives every time, it's doing iterations. So this was regular Hadoop with MapReduce and then basic Spark, and then I've got I found this here. You can have a look at the Apache Spark versus Hadoop page here. But the Spark with some controlled partitioning, some optimizations on exactly how the data is partitioned, and can do quite a bit better in terms of the iteration times. And this is a number of iterations and the total running time. And there is some information here. And basically it's just showing it's a lot faster, right? Because it's now being all kept in memory, which is what you would expect. So here's just an example of word count. This is word count using Spark. So it looks a bit simpler. So there's a text file, which is so we're constructing an RDD, which is just strings, right? And that comes from Hadoop file system. So we're reading some sort of file here. It's not a full example. There's obviously some initialization and stuff, but just for you to see. And then from that RDD, so from the text file, so there's a dot, right? Text file dot, so we're calling a method in there, flat map. So this, for each of the strings is going to split it up on the space. So just split them, and then create an array, right, as a list, and that will be the output of this. Now this is Java
1.8, which gives us the lambda functions that we're seeing here. So if you haven't tried Java 1.8 lambda functions, you should. So you might not see this as regular Java, but this is Java 1.8, right? So for each of the S, then do this operation that comes from the text file, right, which splits it up into words, and then map for each word, then create a tuple, which is very similar to what we saw in the word counting from the previous MapReduce, where we just said for each word is a 1, that comes, so that's the map, and then there's a dot here. So this is just really it's really just creating. It's saying on this RDD, which is called it's creating a new RDD, but on this RDD text file, it's applying these transforms, right? First a map, and then another map, and then a reduce by key. And this reduce by key is it's reducing when it's a specialized function. It says for the same keys you take the values. Here are the values, and we add them together. So this produces a string integer pair, which is the key, which is the word or whatever, plus the count, which is an RDD itself as well. So we've taken one RDD, we've done a transformation to it, and created another RDD. Yeah. And then the counts, then we can save as a text file, and that's when we would write back to HDFS, right? So this is just a very small program to do word counting. And each of these transforms, there's only really 2 RDDs here, but they, the intermediate would you keep in memory. Here's another example I found it kind of interesting. It's not doing any reading from the disk drive, it's just showing you computations. So. And it's estimating pi. Now it's using the Monte Carlo method, right? So where you just throw darts at a dartboard, which is a unit square or something like this, and it has and you look at the number of darts that are within the radius, right? And the ratio gives you the estimation for pi when you multiply by 4, right? Something like that. And so to do that, first we create this array. And then again, it's using the things from Java 8, but you can parallelize the array, and then for each element of the array, you can do this operation. There's no I in here. It's just sort of saying for each element, do this operation, which returns a true or a false value. So you end up with an array of trues or falses, and which you can count up. So the operator really is just the count at the end, and then print out, So this kind of thing can be done, it's just a basic computation. A little bit more complicated thing is, maybe spam detection. Now here, so we've created a number of RDDs, one between, so what's the Spark streaming here? So we didn't really talk about yet. We'll talk about on the next slide, but say there's some stream of emails or something like that coming, then that creates an RDD, and then that goes through perhaps some process that's transforming that data again into another RDD that's maybe being, now there's some other kinds of ways to put into Sparkle, it's called, to put into a database potentially to query, and that maybe creates another RDD, and and so on, right? So the transformations, each one of these RDDs is different. Remember, it's kind of it's read only, right? So you don't really modify that. You can add to it, but you don't update these sets. So what's the Spark streaming? So the people, we're still using MapReduce. We still have these RDDs as a concept, but we need to do some sort of streaming as well, because we want to be able to process the data as it comes, and potentially come out with something in real time. So the Spark streaming concept is that you have an input data stream, and that could be coming from any kind of place. It might be coming from a Kafka, which is a publish subscribe system. It just generates data. You publish data, you can subscribe the data. Or other places, I don't know this, I haven't used Fluent very much, or Kinesis, or maybe just a socket. You're just reading data from a socket from somewhere, right? In our case, a lot we just read tweets. We go to Twitter and they just give us an endless stream of tweets that come from all people tweeting. So that might be coming, and then it creates batches of input data. So these and it's called a D stream in Spark. So, but these D streams are just represented as sequences of RDDs. So little RDDs, each one of them, you know, is like a batch, and each one is seen as an RDD that then can start to be processed by the Spark engine. So the notion of doing streaming is that you create small, or sometimes called micro batching, small batches of data that you then pass on to the typical MapReduce. So the data then gets mapped out, and the reduce, you know, and you go through your process. Now, how small can it get though? So, you know, you can't get all the way down to a single data element, or otherwise maybe, you know, there's really no parallel processing for, you know, the mapping doesn't necessarily work, and so you need enough data in there to make sense that you can compute something for that RDD. So you can't make it too small, but you don't want to make it really large, because the bigger you make this micro batch, the more latency, you know, you sort of got to wait longer before you can produce an output for that particular batch of data. So there's kind of this is the concept they applied to try to do streaming with batched data. You know, the whole thing is based on batch data, but we just make the batches really small. But we can't make them too small. But later, if we get time, I will say as well that another approach that's taken where, you know, we don't even look at batches anymore, right? So to do streaming. So anyway, so there's the batches and then the Spark, and that's processed, right? So here's another slide that sort of shows the same thing, but, you know, a bit more detail. So a D stream is a sequence of these RDDs representing a stream of data. So here's an RDD. So this is a batch for a time interval from 1 to 2. Here's another batch for the same time interval from 1 to 2. It's in the same interval of time, and then, you know, for a time interval 0 to 1. And each of these things then are the partitions and can be mapped out, right? So this is sort of one D stream with the RDDs, and then, you know, when you transform it, you're really transforming it, you know, a sort of a micro batch at a time, or an RDD at a time, and creating then so here's some input D streams, some lines, and then the output, maybe, you know, we call it sensor D stream. I don't know exactly this example, but, you know, so for each one you're sort of then creating another stream, right? So just like before when we, you know, from one RDD we created another RDD, you know, in this case, for every one in the stream, we're doing the same thing, right? So we're doing it in that sort of way. So that's the concept of Spark streaming. And here's just a little bit of code just to sort of maybe make it gel in your mind a little bit. What you might do if you were programming in Spark streaming, right? Again, it's in Java, but they have Python and they have Scala examples as well if you program in other languages. So there's some sort of configuration that comes up first that just sort of says how many threads do we want. And as well, I didn't mention before, but there's the notion of the interval. So the interval sort of tells us how big should these batches be, right? You know, in a sense, right? So it's sort of saying how long do we want to wait before we say, okay, you know, this is the size of the batch. And in this case, you know, that's sort of set at, you know, a batch interval of 1 second. Now, it's this aspect here that later when we talk about Beam, Apache Beam, that we'll talk a bit more about, because actually this is very grey, just setting a batch interval of, is that 1 second of system time? Or is that 1 second of data time? What exactly do we mean by this second? And I think here you'll find that it's 1 second of system time. So every second the system, you know, will sort of tick over and create a new batch and so on, right? So you create that, and then you need some place where the data comes from. And in this example, the data is just coming from, it's a text stream. So we're connecting to a server somewhere, and that server is just sending us lines of text. That's what it's doing. just sending us lines of text. Let's just assume that, and that creates an input, D stream, data stream, I guess it stands for, and then from that, so now from the lines, we're going to apply a transform where we're going to just a flat map transform like what we saw before. But here is the function. Actually, we can override what the function is, which takes some strings. Sorry, it gives some strings as the output, and so what is it doing? It's it's returning an array, and it's just splitting on the space. So it's doing the first part. It's going to output essentially a list of words. So for each line that comes in, it's going to break it down into words, and that will be. So we're sort of just breaking the data down. This is kind of the first step. And then I haven't shown all the steps here, but now onto that D stream you would apply now another transform that might count and stuff like that, or it would apply that, for each word it would create that key value pair where you had word comma 1, and then that would get mapped out, and then the common keys would all come and they'd be reduced, and that would happen on a sort of per RDD, per batch kind of basis, right, for us. So the Spark is taking into account all of the, you just have to really specify these simple things, and all of the micro batching and all of that stuff will sort of happen. The distribution will all happen for you. All of the stuff we talked, in memory, it will, it'll optimize for you and try to do this process. So this process will just continue to then create at the output, the final output stage would be, for each batch, for each interval of time that we have, what is the frequencies of words that would write that, and so your output, you would see files that were being created, for each of the intervals that we had, that might go into a database perhaps, and then somebody's perhaps querying that and seeing in real time, each second, what are the highest scoring words or something. So it might be trending terms or something like that you want to see. Right, so that's kind of what the application of this sort of thing. So what I think you can see is that that Apache Spark is it's very it's very simple. You'll find it's a bit simpler than programming with MapReduce. It's more expressive. You might have a little bit higher learning curve to learn that, but you'll be able to write programs a bit easier. So the code size, so here are some other, so MapReduce, so if you were to write a MapReduce, Hadoop MapReduce program, here's a typical code size, and here's like a comparison, with Storm, which I might talk about a little bit later, but here's Spark over here, and the code size, and Giraffe is a graph processing engine, and Impala, which is SQL, of the non-test, non-example source lines actually in the package. So it's kind of more efficient in that way. It will run on top of Hadoop 2 and Apache Mesos, so you can sort of install it on here, or you can run it separately as well. So you can go, and it's another exercise of installing and like what we were doing with Hadoop, and try it out. So it integrates really well on that platform, and you should be able to do that. So it's written in Scala. It's just got a summary, but as I said, it's got Java, it's got Python as well. If you do that, and here are some of the other things that kind of go along with it that we talked about as well. And we've sort of mentioned some of these things in previous lectures, but so that's Apache Spark. Are there any questions about that? I think it at least, maybe it suggests some things for you to think about from a coding point of view, how you might start applying it in different ways. So Apache Beam is quite recent. It's very much along the same lines as Spark. It's trying to do the same sort of thing. Apache Beam provides a unified programming model. But it solves certain things that we were actually doing research and trying to solve as well, that were quite unclear about
stream processing, in particular real-time processing of big data. Everybody was doing differently, in the different camps of people building systems and doing the processing. And I'll just sort of illustrate the problem that, there's I don't have a copy of it, but there's a seminal paper from the Google guys that sort of talks about Apache Beam. You might be able to find it, or I can give a link to it. But one of the problems that they had was that Google needs to bill its clients. Its clients tend to be advertisers. That's who, where it makes its money from. And the advertisers like to put advertisements into video. So if you're watching a YouTube video or something like that, it will come up with an advertisement for 30 seconds or whatever, or things like this, right? So, and what Google needs to do is it needs to add up all of the times that people view the total time of the advertisements that they've watched. So 30 seconds plus 15 seconds here plus another 30 seconds there, and say, well, this person viewed 2 hours of advertisements, so we're going to bill you for that. You paid us to advertise to these people, so we need to add this up, right? So then they need to send that out to that bill out. And the problem they have is, if you think in a timeline, and you can think, let's just divide it into days, right? So this is day 1, I don't know, day 2, day 3, right? This interval of time, right, is a day, and here's another day. And here's another day. Now, what they want to do is sort of at the end of the day, they want to sort of calculate the bill and send it off to the advertiser. Say, here's today's bill, right? And here's another one at the end here. And each day maybe add up. Now, but what's happening is that the people looking at the videos, maybe they watch on their mobile phone. And they're offline, that they did watch advertisements, but it's not being reported. So actually, if you have if I draw another timeline over here, and we sort of put ticks where a certain person might have watched advertisement. This is the actual times when they watched an advertisement of something. But the information about this doesn't, maybe it gets to Google here, and maybe that one doesn't get to Google there. Maybe it actually doesn't come till like over there because, in the meantime, this person they were disconnected, although they were still writing. So what's happening is that this we might call the application time. Application time. And down here is the system time. And the application time, when things actually happen and when data arrives at the system, are two different things. They get delayed. So another way to look at this is if you have system time on the x-axis and you have application time, maybe the other way around I want to draw. Actually, I want to draw application time on the x-axis and you have system time on the y-axis. So if the event got to the system exactly the time that it was produced, then all the events would be on this line, right? So an event like something data that's important, it would be on the line. But if it's delayed a little bit, so that usually there'd be some delay, right? So actually events will be above this line when they actually arrive at the system. So these delays then sort of affect the accuracy of your data calculation, of your bill. So if we're billing somebody now, we don't have all the right data in the interval of time that we need. And the question that Google started asking was, well, because this is a particular kind of windowing. This you could think of as a batch, if you like. The batch for today and then the batch for tomorrow, but we talk about windowing, in time, right? And this is what we call a tumbling window. We've just moved from this day to the next day. It's not a sliding window where we kind of go like that, but a tumbling window from one day to the other. The question they started asking is, well, how can we write programs and do big data processing in such a way that we know what the errors are and we can trade off between,
accuracy of computation, right? That we, and latency in giving the bill. So, for example, I could give you the bill today, but it might not be very accurate. But if you're willing to wait a little bit longer, then I can make it more accurate, because I know that more data will come later. So, before with Spark, we saw the notion of defining, say, a 1 minute or a 1 second batch interval. We just said, oh, well, every second the system will just output the result. That's all we said. And there was no notion in Spark of, well, did we get all of the data for that second, or what is the data coming in that second anyway? Is it old data so if we were computing in this interval, the bill, and we got that piece of data came later, then we shouldn't add it into that interval, right? It should actually be added into the previous interval. So there's this complication where you can't just be thinking about stream processing and this batching of data as just whatever we're up to now, and we'll just take whatever data comes and put it into the batch and process the result. But we need to hold on to a certain number of previous batches for a certain amount of time before we output and go to the next result and continue down the pipeline of transformations. Or indeed, maybe the final result can always sort of be updated all the way through if we get some data that's old, that's come after we've already moved on. But how do you express all of this at a programming level? Right, that's the question. So Spark really didn't, and a lot of people weren't really thinking about the correctness. And we have the same problem that, we report to somebody on a screen as a result and say, here is a graph and it represents tweets in the last hour, all of the people that have communicated in the but what does that mean? Which tweets is it the last hour of whatever tweets came, or is it the last hour defined by the timestamps on the tweets? So again, data, when it comes, it has timestamps, and there are ways of, you can think of the last hour of system time, whatever came, or the hour defined by the timestamps in the data, which becomes a bit harder, because then these windows of these batches you only kind of create when you get data that has certain timestamps. So all of this discussion, which is creating a lot of questions in your mind, how do we do all of this, is what Apache Beam has been built for, right? How to express it in such a way that they know that their calculation at the end, they have some guarantees, not just on accuracy and latency, so that there's a trade-off, but also on cost. So they can always add more resources to make the computation faster and maybe reduce the latency and say, well, we can produce the result now faster. But again, that is another axis of trade-off. So, do we want to purchase more machines and so on, or not? What is the trade-off there, right? So Apache Beam is all about that. It's what are we computing and where in event time do you want to process? So what do we mean by all these things? And it's quite good. But as I said, we were doing research where we were looking at windowing and correctness, and all of this kind of thing. And we had published some work in this space as well when Apache Beam came out. But from a programming point of view, it's somewhat has the same concepts as Spark. It has something called a pipeline, which is your sequence of transformations. Instead of a D stream, it has a P collection. Or instead of an RDD, really, it has what it calls a P collection, which is an immutable distributed data set. It can grow and for the pipeline to operate on, right? So you have a data set in the same way, and then you have a bunch of transformations in the pipeline. So, filter, group, analyze, and so on. And the transformation will take a P collection as its input, and it will produce a P collection as its output. The same as the RDD examples that we saw. And then similarly, you have sources and sinks, right? So the data your original P collection can come from reading a file, something from HDFS or from a socket or whatever, and then there's a bunch of syncs for writing to databases or just files again on HDFS. So conceptually the same kind of approach to writing programs, but with a lot more expressiveness around exactly, what are we computing, right? And when should we go on to the next batch? And how accurate is that, and so on. So the flow of a beam, you create a pipeline object, create a P collection, start applying transformations to it, and you output. It's basically what we just sort of said. You run the pipeline. The thing is that I might add, and I didn't say, is that this Apache Beam is really the goal of it is to define an API. It's not really to build a distributed processing engine. It's really just to define an API, which is the way you express what you are computing. The API can be implemented on many different things. Right? You could implement it, so they call kind of runners here, right? So, Spark runner, you could implement it on Spark, or you could implement it on MapReduce. These different things, you can, implement it depending on what exactly the best underlying execution engine is for what you want to do. So if what you want, the kinds of computations that you're doing are very much suit a MapReduce approach, then that part can be run on, on a MapReduce or Spark or something like that. But if it suits more an incremental, very much stream processing, which I haven't talked about yet, but I might add to the end if we have time, then you can sort of dynamically choose that. So the program can be then, at the scheduling level, can be kind of run on different things to suit the calculations, and that sort of separates the semantics, right? This is what we want to do from the implementation. This is how we do it, right? So that's again, the direction that people are going in this space. It's a bit more of a software engineering kind of discussion, but it's a way that the direction people are going. That my colleague that I work with a lot, Shanika Karanasakara, she's a software engineer principally. So that's kind of flow. So there's a pipeline that has some options. Maybe you create a pipeline somehow, and I don't really have examples of the options, but then you go and apply transformations to it. So the stream that you might apply a parallel do of set timestamp and extract text. So there's some class that will do something in parallel, and then to that outcome you will apply another parallel operation which is extracting words. And then to the outcome of that you will apply a counting thing that will count per element. So this is very much written in the same way that you would, the Spark program would be written. Each one of these applies is really creating another P collection. It's just that we're operating on it immediately with another transformation. The outcome of all of this is a P collection. So the parallel do is very similar to the MapReduce. So it's doing something like that. You can group by key, you can combine things. So it gives you a range of ways of expressing the very much exact, the kind of calculations you want to do, flatten and partition. So the P collections, they can be partitioned out and broken into for parallelization, or they can be just flattened. And, so there's a whole range of things that you can do to these collections of data, right? So here is an example of that extract word length, which is a function. Extends this function on string and integer, and again, it's just doing what we've seen before. These word counting things. It's splitting up. Here, the split is a little bit more sophisticated because it's based on a regular expression of some kind, and splitting up. If the word isn't empty, actually, it's outputting the length of the words. It's a little bit different, right? It's outputting the length of the words. So maybe we're looking at average word length or something like that we want to calculate, So, but now the interesting thing with Apache Beam, and so just what we saw before looks very much like Spark, but now comes the fact that they really understand windowing in this, and you can really express what it is that you want to calculate and how. So you have a whole heap of ways of dividing the collection up to do the windowing. And the Spark was somewhat quite simple. Maybe they've advanced it a bit now, but I guess Apache Beam has taken the forefront. And where we just had sort of tumbling windows. Here's an interval of time, and you collect, and then you go to the next interval. And so it wasn't a sliding window. So another thing you can do with windows is you take a window, and it might be 10 minutes, and you move forward by 1 minute. And then you move forward by 1 minute. And each window is, there's a result for each window, right? So it's more, so windows have a slide or an increment that if the slide is equal to the size of the window, then you're just sort of stepping in, it's called a tumbling window. So, but these things you can kind of control. So this P collection is otherwise just one big collection of data. But if you want to break it down now and you want to say, well, I'm not just looking at the data as one big collection, but I'm looking at it in time, right? I want to produce results coming out of the pipeline, if you like, at the end in time, right, in a windowed way, then you can define that. So fixed time windows or sliding windows, calendar-based windows that are maybe just, each day you produce something, or, a single global window might just, I think it may be the default. But the other thing is that you can do is that, you have to think about when does the window move on? And there are different kinds of things. So you could say, I want each window to have 1,000 data items. And when it fills up with 1,000 data items, then I move on. Then I increment the window, right? So that the trigger for processing and for moving on to the next window could be just the number of data items that you have. Or it could be time-based, where you're using a time reference, and that might be event time. So, when I receive a tweet that is beyond the time for this window, the timestamp on the tweet is beyond it, then I move on, right? That triggers me to then say, now I need to go to the next window, I need to slide on. Or it might just be that the local timer on the computer, it's just system time. Whenever the clock on the computer ticks to the next minute or whatever, then we move on. So there's a whole range of different things here. And you can have composite triggers, obviously, when something has happened and something else, and we have and so on. So it's actually quite expressive in this space, because this is one of the areas where everybody is processing big data. They were all doing differently, and they were all doing it ad hocly, however they would. Usually it would just be the research assistant or the postdoc or whoever was doing the programming would have to do some windowing, and so they'd just solve it somehow. And so every system sort of came with a different approach, and that's something that needs to be obviously stamped out and somehow unified, and that's what Google has done with this, and that's why they've released this sort of thing. Yeah, the Apache Beam comes from Google. There's a good paper on it. Perhaps I should find and circulate it. So they talk about watermarks, and emitting the contents of a window after the watermark passes the end of the window, which operates on time, right? So which is one way that obviously you would think about doing it, and based on the timestamps attached to the data elements, or when the watermark passes the end of the window. I don't really have time to go into watermarks, but if you have a look at some of their papers, there's a lot of description there about how that works.
Watermark is some...
It's basically where we're up to in time, in terms of the data that we've received. So another question is, there's so many questions here in the processing. When I'm processing a window, when I move on to the next window, do I just throw the result away from the previous window? So is each computation of a window completely independent of the previous windows? Or are we accumulating a result as we slide along, and each window maybe is averaging from previous results and so on and so forth? So these questions come up. Do we want to do that? And so we need ways of either discarding results or accumulating, right? So here is a a kind of complicated example of a word count example. It's a sort of a full example in Apache Beam. You know, that actually I think my student wrote, you know, Twitter stream. So it reads, actually it's just reading from an input file, which is just a big, you know, maybe a gigabyte of tweets or something like that, and then applying a parallel do and extracting words and so on. But you know, the interesting thing is the windowing, right? So now we can sort of say, well, I want to take this data set, which ordinarily is just considered one big data set or just an endless stream of data that's coming. It could be unbounded, an unbounded data set. It just keeps coming with more data. I want to take this data set that I've just done these transformations on, and you know, I'm going to divide it into fixed windows of standard minutes of 5 minutes, right? And then I'm going to trigger the movement of the windowing with a watermark past the end. So whenever I get a tweet that's past the end of the 5 minutes, you know, but I'm going to allow some early firings, and I won't talk about, you know, the after processing time plus a delay of and with late, you know. So there's these conditions that you can say. You can see it's quite expressive, and we won't really go in and talk about all this stuff. But you know exactly how the window gets moved on. And then for each window we'll count the words, right? So with this kind of expression, when we get a result for a window of data, we know what it means. You know, we know what has been done to compute that result. It's not just arbitrarily whatever data arrived at the time we were computing, but it's very specific. Well, the data is in the pipeline, right? So there's a pipeline. And that was reading from a file in this case, but it could be coming from a socket. So this thing is reading a tweet at a time. And then we're applying this function extracts the tweet text from each tweet that comes, right? So if this is coming from a file, the file will have tweets, and the metadata for the timestamps for the tweets will be in the tweets. So this calculation, if it comes from a file, this will eventually end because it's a finite amount of data. It's a bounded amount of data. It will come to an end, but it will output a bunch of different results for each window of time that you know you'll get a count of things. But if this was reading from a socket, from the live stream of tweets, then this thing would just keep running, outputting for each window. And, you know, the data is being, you know, affected. It depends on what you run. If you're running on Spark, then if it's a MapReduce type thing, then the data is just pipelining through memory and you know, the windows and so on. And I guess trying to bring it back to coding, you come back to how is it implemented. It's being stored in distributed memory. These things, as they accumulate the data, you want that to be reliable as well, and so on. So you come back to those things where this sort of system relies on the data and everything happening in a reliable way and an efficient way underneath. Now, I don't know how you could connect this to coding in some sense, right? The expressiveness of the program. That is something really that is still like for, you know, discussions and sitting by the fireplace. We sometimes say a fireside chat, and you know, talking about what can we do. And I don't know, but this is effectively the latest sort of thing that has come from Google and the directions in terms of streaming data processing, right? So you could have a look. Actually, this is the paper. I think this might be the paper that you can have a look at. They call it a data flow model. It doesn't mean data flow computing from the 80s or something like that, but it, you know, and so you can have a read. It's a VLDB paper, and you should be able to find it there. And that will tell you more of the details. And this is, so that's Apache Beam. Now, all of the discussion though is kind of been around batching, you know, and really there is another approach. I'll just add it. I said that we use, and that's Apache Storm, you might have heard. Apache Storm has a completely different approach, it doesn't do batching at all. There's no batching. So what Apache Storm does is, sometimes I call it topology-based computing. You have operators that operate on streams of data. So you have tuples coming in, potentially key value pairs, and the operator maybe does something and creates another stream of tuples that goes to another operator, and that might then send out in some way to what we call a bag of operators that are all doing the same thing, and that they might come back to an operator and so on, and we construct like a directed acyclic graph of operators, and the data flows through these operators, and it flows one tuple at a time. So there's no batching. Each individual tweet comes in, and then something happens, and some output comes out. This is potentially a different tuple. It might be a set of tuples. This is like a map reduce. So this operator might be mapping out the tuples that come. And in fact, Apache Storm, Apache Spark, MapReduce, they're all the same in some sense. When you start looking at what's happening and the way data is being processed, there is something about them that's very much similar to the same. So the same sort of MapReduce, the difference is that this is Apache Storm is all for incremental. Each piece of data that comes, we process it immediately. So it has a lot of reliability as well. It does do replication of state for reliability, and there's quite a lot of research in that. If a node is to fail, we need to be able to restart it. So it might have some state involved in it in that node. So there's research in that space. And we would be using Apache Storm largely, and then we do windowing as well, though. So we're trying to understand the same problem that Google is solving in terms of windowing, but understanding it from a stream processing or a topology-driven processing point of view. Now, I might say that the Apache Beam, as I said, that's just an API. It can run on other underlying implementations, and presumably it could run on on this kind of implementation if that was optimal for the kind of processing that needed to be done. And there's different camps of people. Some of the camps of people are saying this is the way we should build our stream processing, this is the way it should be done. Other camps going the Spark path, the competing, as you would have in other areas, competing groups of researchers trying to see what is the best way to process data in real time, big data, and get results and so on and so forth. So there's just so much to say here, and that the course is really not, obviously it's not about the processing and so on, but it's interesting to see how codes might be applied in that area as well. If you want to know more, you can obviously find papers, and I can help you find some papers on Apache Storm and topology-driven processing, we sometimes call it, right?
Does it still use the memory hierarchy that you mentioned, SSIDs?
Well, there's less. So the question is, does it still use memory hierarchy and things like that? It doesn't talk about data sets so much. So you might not find that concept is there, but it does talk about states of these things, and so some of the solutions are we store states in a database to recover from. It's hard to see how you might get the coding theory applied in this space.